Hello, welcome to this advanced section of Creo or BMX Behavioral Modeling Extension. Today the task we have is we have this model, a simple model, and we want to determine the minimum cross-section area, and we want to set that minimum cross-section area to a certain value. This model is already optimized. This surface you see here, that is the minimum cross-section area, and if I go to analysis to area, I'm getting exactly 1000 millimeter squared. How can you perform this type of analysis to determine cross-section area and set it to a certain value? I'm going to go back to how this model was before being optimized. This one was 100, was like that. That's the, now, now my model here, if I measure that area, I'm getting 1520. Let me just save this area here for you to view that to be there displayed. Okay, therefore, I'm going to perform this analysis from scratch. Simple, just model a simple body. You can have a surface or a body, whatever you prefer. I've used a sweep, and this is how it looks like. Let me show you the sketch. I just made a simple sketch. Yeah, this is my simple sketch. I made it here like that. This is a, yeah, make a simple sketch in case you want to practice. Then step one, I want to calculate the cross-section area across this model. If I go back here, then now I can know this one is easy. This one is easy to calculate because I know if I measure this, that is 30. If I measure this, that is 70. I know at this point we have 30 times 70 and 100. But because but as you progress, as you can see, we are using a curved surface. You may not be able to do that, assuming this one is a very complex geometry. What do you do? What do you do? These are the steps you should follow if you want to perform analysis of your design to determine the minimum or maximum cross-section area across your model and set it to a certain value using sensitivity and feasibility through optimization study. We are going to use these three to perform that analysis. And today we are going to use what we call UDA, user defined analysis, whereby you define your own analysis that will be executed by Creo. And the first step is we need to create a point onto this curve or this one of them because we want to create a cross-section area across complete part. Therefore, if you go to model, we have this point, we have a point, this is the normal point, a datum point, we have an offset coordinate system, but today there's a one called field. Create a field datum point. A field datum point, this is a point that can move across your design. If I select field, I just need to select an edge. To be sure, let me just use edge of this edge here, like that. Therefore, the problem of using this, I don't want to select one edge. Let me just remove. Let me just use my sketch instead to be sure I'm selecting everything. Let me use what we call curve. Yeah, to be sure I'm correcting. You can see now highlighted green. I'm sure now this point can move across this green highlight and say, okay, we can give it a name, field point. Field point. Those people who like naming their features like me. I have some, let me just delete everything that is here. Let me just delete all this. Okay, at least now I've deleted to avoid confusion. Therefore, as you can see, I have this point. It's called field point. Field point is a point that can move across your edge. But if you use the normal edge point, this normal point has to be constrained like that. This point can't move. It will always be there. But this point can move across the edge or surface. Those are the differences between the normal datum point and your field point. Then I need now to create a plane that is passing through that point. Let me show this. A plane that is passing through this point and parallel to this. Therefore, select these two and create a plane. Let me just use a small in size. Yeah, like 30. If I can hide this. Then if you view from top, you can see this plane is parallel is across it is cutting through the model at the same time passing through this field point. Therefore, this point can easily change. I don't need to use any dimension. You can just drag the point and your plane will always update. Therefore, the analysis will shift this point across this edge, then calculate the cross-section area. And for ease of visibility, I'm going to create a field surface that represents the cross-section area. Therefore, first thing I need to do is I'm going to select quilt, this one here, go back to the geometry, press Ctrl and select your plane, then select intersect. Intersect means that this plane where it intersects with the quilt, it creates this datum curve. And using this datum curve, I can now do a field surface. Just select that one here, create a sketch, that, um, okay. I need to project that, close, see okay, then fill that. This surface here, let me just give it some appearance for ease of visibility. And maybe I can hide that curve and now can hide the plane. This one you can show. Let's just hide this curve. Okay, let's hide it from here. Now you can see this surface represents the cross section, and this surface can move across your model. If you change this point, maybe move it like that, my field point, this point there, you just need to move your point and it creates a new surface. And you'll see that this new surface, if I go to analysis, go and create area analysis and do a save area like that, close. You see now the area is that 118. If I try to change this curve, it is still displayed. If I move this point here, let's go all the way the other side, see okay, my area is new. Therefore, we want to determine the minimum area of this model, then set that minimum area to a certain value. Assuming you want to determine you're designing a pipe that's supposed to carry certain fluid or certain anything, and you want to control area at a certain section, you can do this. Okay, that's the first step. Therefore, I'm going now to next is I'm going to just go back like that because you need to have a field point. You need to have another one called datum, the datum plane. Then you need to have analysis. I'm going to perform now analysis of area. Therefore, basically, let me just go back here. Let me just go to save the analysis. I don't need all this. Just remove them. Then perform another analysis of area of this. And I'm going to give it cross section area like that. And instead of save, make a feature. Okay, I have to rename again here. cross section area. Then say okay. And for here, I'm going to get area. If I close this, if I go here, I'll get the area. You can see the area is in millimeters squared here. Basically, just right click here, go to the information and select feature information to see the value of area, that is 1790. Therefore, step 3 is you have to select all these items here from field point to analysis like that and group them. And you can say area calc, maybe calculation is your group. You group them. UDA, user defined analysis, must use a grouped items. If you go to an user defined, you can see area calc. In case you have another group, it will appear here. Then references, these are default for now. Calculation settings, the parameter you are calculating is area because this one here analysis is returning an area. You can return an area. You can return maybe principal moment of inertia. You can return a length, maybe diagonal across that. There are so many parameters you can return. But for now, the most commonly used is area. Domain is we want to calculate area across full domain. The reason why we said we're going to use a field point because field point can move across full domain. Hence, but if you want to use a specific point, you can select at this point, do the analysis. But you can always do that using field command to get that analysis. Therefore, here use entire domain. Just leave this one. These are just resolution, accuracy, because this one will generate some graph here. This graph will be generated. Let's have a high accuracy because it's a simple model. They run very fast, and you can say compute. Okay, you can see the graph I talked about. This is a graph. This graph represents the area at a given cross section, but is magnified, and it returns minimum value of 1520 and a maximum value of 39.592. This is my main interest today. You can also perform a maximum. Maybe you want your maximum area to be a certain value. You can also use maximum. But you can as well can use combination of minimum and maximum. You can say make sure this is the minimum, make sure this is the maximum. Therefore, we have seen our minimum is 1520, but maybe I want this one to be exactly 1000 to be my minimum. Therefore, here I'm going to save this as analysis, like here. For me, my focus is mean area analysis, like that. It will return minimum and the maximum, but for me, my focus is mean area analysis and add feature. It's called mean area analysis, like that. Say okay. You can see here it is. If I say close, if I go to information, feature information, if I scroll down here, I see nothing. There's no data. Where is my area? Okay, what you can do, just right click here, go to edit definition. This is now the analysis whereby you define what you want your analysis to report back to you. And these are called result parameters and result datums. Let's go one by one. Result parameters. You want user defined to give you minimum value defined. When you here you can see minimum value create, you have said no. You have to double click here and say yes. Minimum. I'm not interested in maximum, therefore I leave it as no. If you want maximum as well, you can just say yes. Again, I want For the datums, the minimum, I want to have a point. This is the field point, a point to be created on this curve that presents the minimum. Therefore, I'm going to double click and say yes, create a point for me. Okay. If I say, if you want to graph entity, let's see what happens. This, see, okay, it creates a point for me. You can see you have a point here that is created. Therefore, if I go back here, you can see now this one is defined. We have this point, and I was to go. Okay, let me just cross here, cancel. Yes, I was to go to here. I was to go to this here to see whether we have the value. You can see minimum value. We have our value. It is a local parameter. Local parameter is a parameter that exists only in that feature. Therefore, if you go to parameters here, you need to see that parameter because this one is a local parameter that exists only in that feature. Therefore, I have this point that coincides with the maximum minimum area. And if you want to validate that, you can create a plane at that point there to see whether it is true. The area is 15 something, 1520. Then as I said, you can go to model, you can go to quilt this back to mod geometry, this plane here, and do what we call intersect. Then you can sketch here and you can say project, out rotate, so to select this project loop. Yeah, that, and I can say fill that area. If you can see, we have this fill body, fill surface. Let me just go to view. I like changing my view for ease of visibility. Can use that. If you now perform analysis of this one here area, you see we're getting 1520 because this is the minimum area that is being returned by our analysis here. Our analysis UDA, user defined analysis UDA here is returning 1520. Therefore, I want to set this 1520 to be a certain value by changing the this dimension here. I want to change this 100. This 100, you can change also this R40. You can change 70, whatever you want. But for me, I want to change the R100. Yeah. Therefore, for me to do that, I have to go now to sensitivity analysis. I want to see because if you don't perform sensitivity analysis, you'll see that once you perform that, there's you this 100 has a limit. If you make it very small, you'll see has an issue. If I say 70, you see it can't. If I say maybe 105, yeah, that's fine. But when I try to say maybe 200, you see the section. Let's go back to 100. Therefore, because you can't be able to know what happens when your 100 is changing, it's good to perform sensitivity analysis. It will recommend, you will see from that. Let's perform sensitivity analysis. And my parameter, I want to see how parameter is changing when I change this dimension. I want to change this dimension from, let's go from 50 maybe to 150. Let's see that range and use 50 steps or 51 so that we can have one full value instead of decimals. Let's compute. Let's see what happens. Yeah, as you can see, now it's performing sensitivity analysis and it is plotting minimum cross-section area on y-axis versus the value of radius on x-axis. As you can see, below 80, we have a problem. And that when you try to use 70, you get error, you get issues. That is below 70. Let's see what happens when you go above something value here. Maybe, yeah, let's say we are at 130, 120. But here is very clear that anything below 80 will have an issue, because you can see we don't have, the model is breaking below 80. But above, as you progress above 80, now we are getting an area starts to decrease, to decrease, to decrease. Therefore, this graph, as you increase the radius, the graph tends to zero, meaning the value of radius should be between 80 and a certain value. Otherwise, you're going to get an error on your model. As you can see, our graph is now dropping. Now this zero area. As you can see, parameter evaluation failed for some values. Yeah. Let me just take a screenshot of this so that I can explain what is happening. Let me just close here. We saw what? At least at 80, we are getting a graph. Let's try to use 70. Let's try to change this to be 70. Let's go to here, try 70 or 75. They can't. We can't get that. This radius, because of this 70. This 70 is tending to pull this back. Okay, you can see. Let's now try something like 150 to see what happens. Let's try this first. Try 140. 140 is okay, but you see, the more you increase this, these are going to intersect, cross each other. Let's go 150, almost touching. Yeah, but we are getting something there because we have a dot. You can see we have a small dot there at 150. But let's see what happens when you go maybe 152. The model fails. They can't. Therefore, you can see from this graph, you can be able to determine the point at which your analysis or your dimension here is going to fail. It should always be between 80 and 150. And for me, I want to find a place where I can get 1000. I want to get exactly 1000 area, and I can see it is around here at a certain value here. I'm getting 1000. But how do I get this value? At least I know it is between 110 and 130. It's between those two. There are two ways we can do. There's one we can do this. That is called um, sensitivity, feasibility, and optimization. And they say it is between 110 and 130. Maybe depending on the model geometry you have, you want to narrow down this range. Instead of using 110 to 130, let me narrow down. You perform another sensitivity analysis. Now I know it is between 110 and 130. Here I can just use 21. Now you can perform a very quick analysis to narrow down this value, yeah, more. You can see now it is we have no error because our radius value can be between 110 and 130. We are performing a second sensitivity analysis because we want to narrow down close to the actual value, so that once we perform feasibility and optimization, we can use almost accurate value. It's very good to perform sensitivity so that you can get a range of where your dimensions will be. And you can see I'm using 21 steps so that I can get a full number 114, 115, 118, because I'm getting 130. minus 110, that is 20, then plus 1. Plus 1 because we are going where it starts, the first point. You have to use 21. If you use 20, you're going to get 110 point decimals here. Now, I can see from this analysis, I've narrowed down to this point here, 117. If you put your cursor here, you can see it is between 117. Therefore, I'm confident my value is between 118 and a value here. Maybe you want to narrow down further, you can just go here and change the scale on x-axis and say, here cell up, let me just use a maximum of 120, minimum of 115. And use how many steps? 6 steps, like that. 5 steps. Now I can see at 1000, now I can now narrow down here, I can see where that, let me just screenshot this. This is red pen. I can see at 1000 here, I need this point here. That is between 117 and 118. Therefore, I have two values that I can use in my feasibility analysis. That is 117 and 118. Go back here to 117, 118. Here, feasibility, dimension. Come here, select this one here, 117, 118. Yeah, I have to say that so that I don't forget. Enter which parameter add. I want my minimum cross-section area to be exactly 1000. Okay, cross, go to options, preferences. Okay, I want to graph constraints and variables and the convergence. This is the error. You can't get exactly 1000. You need maybe an error. Let me use 0.001, a very small error there, and I can compute. Therefore, because now I have narrowed down my min and max values, the analysis will take less time and it will be accurate. Yeah, completing step 1 of optimization. It is performing now second step and it will get the value for the, yeah, you can see during the uh, second optimization here, it was able to find a feasible solution. That is just one step here. And then it performed another step to confirm. We have the first step, second step, third step. Therefore, if I close here, I can see it was 117, ramp up to this value, then iteration, then became constant. This one is a variable. Therefore, if I say close, I can say now confirm. It changes this value to 117. And if you measure this area here, if you go to measure area like that, you're getting exactly 1000. Okay, now my model is exactly as I want. Lastly, let me just again compute to show you something. Okay, I can use this one here to always ensure that area is always 1000. Yeah, if you select that, if this area is always 1000, in case you try to change a dimension here, let me try to change something here. This 40. So instead of 40, let me make it, but before I do that, something very, very important. Let me go back here. Okay, let me go back to here. We have to change these values now. The minimum, we saw it was 80, and we saw it was 150. Okay, therefore, do like that. You have to use a wide range. Okay, like that. cross this. Yeah, that's bigger edge, cross now. Therefore, if I try to change a dimension here from 40, let me use 38, smaller value. This ensure area is 1000. It performs now the analysis again to set the radius of this curve to a new value such that we get the area of 1000. It's a very powerful optimization tool. You can see now. Therefore, if I try not to measure this area, let me just repaint here. Let me go to area here. Okay, still regenerating. Okay, some time here. Okay, close. If I try not to measure this area, I've changed my fillet, still 1000. Okay, let's change that fillet more. Let's go back here. Maybe yeah, let's make it maybe something like, let's make it something like 50. Still the model is going to run again. Optimization is going to run the feasibility to find that value and set it such that the area remains as per the definition. This one is a very powerful tool to make sure that your model is smart, intelligent model. Therefore, if you go to analysis, area, yeah, in some time here to regenerate the model because it is now iterating on the feasibility again. Therefore, you can see now it is wider. Let's see the value of area. Still 1000 doesn't change. That's how you can make your model smart, and that's how you can optimize your design to set uh, a certain value. You can do that with volumes, mass, center of gravity. You can do that with a bunch of information. You can also perform what we call curvature analysis. Then you can see minimum and maximum. Then you can save this one as a. You can also you can save these ones here. You can also optimize this. You can do a lot of things, a lot of things using BMX. Thank you and stay tuned for more.